Okay, so if you just stop and listen right now, you can probably hear all sorts of things. Maybe the hum of a fan or someone talking down the hall. What's just amazing to me is that the human ear can handle a range of sound intensity. It's a 10 trillion-fold difference.
That's staggering.
From the quietest thing you can possibly hear to a jet engine. It's an incredible biological instrument.
It is, yeah, but that incredible complexity. Well, that also makes it incredibly fragile and very susceptible to damage.
And that's what we're here for.
Today, we are doing a really critical deep dive into the science of sound energy. We have to move past the common idea of noise as just, unwanted sound.
That's such a key point, because when we're talking about health and safety, the definition is it's clinical. It has to be unambiguous. According to international guidelines, noise is defined as all sound which can result in hearing impairment or be harmful to health or otherwise dangerous, period.
And that distinction is absolutely paramount for managing risk. I mean, think about it. If you're an employee working next to a rock concert, a sound you might really want to hear, the risk assessment has to treat that exposure exactly the same as working next to a loud, grinding diesel generator.
The risk is about the physics, not your preference.
Precisely.
So our mission today is to take all this dense scientific and regulatory information about noise exposure and turn it into clear, actionable insight for you. We're going to unpack the Twitter non-intuitive math of decibels and dose, and then break down the systematic controls used to protect hearing.
Okay, let's get into it. The place to start is the fundamentals of sound physics.
Right.
So noise sources generate pressure waves in the air. These waves are characterized by two main features. First is frequency, measured in hertz, which, that determines...
That's the low rumble of a bass speaker versus the high shriek of a whistle. And the second one?
The second is amplitude. That dictates the loudness, the intensity. And that's where we get into the complicated decibel scale.
It's complicated because it's not linear, right? Sound intensity grows exponentially.
Exactly. Since our ears can perceive this massive 10 trillion-fold range, we have to use the decibel or dB scale to even manage the numbers. It's logarithmic. A linear scale would it'd be completely unusable.
And that logarithmic nature is where it gets so counterintuitive for most of us. A jump of 10 dB might sound a bit louder, but physically?
Physically, that 10 dB jump is a 10-fold increase in sound intensity.
And fold.
And if you only remember one thing from this entire deep dive, it should be this. For pretty much any practical measurement, an increase of just 3 dB means a doubling of noise intensity.
A doubling.
Yeah, and this is so crucial because it shows why you can't just add decibel values. If you have two 90 dB machines running side by side, the result is 93 dB, not 180.
But that seemingly small 3 dB jump means the amount of damaging energy hitting your ear has literally doubled.
It is doubled.
So with that exponential intensity, how do we measure what's actually harmful? Because our ears aren't equally sensitive to all frequencies, are they? We can handle a low bass rumble much better than a piercing mid-range sound.
That is precisely why we use A weighting, designated as dBA. It's all about relevancy. An electronic filter is applied to the measurement to mimic the human ear's own sensitivity profile. It filters out the very low and very high frequencies that our ears are less susceptible to damage from.
So it's like we're measuring the risk profile, not just the raw volume. We're measuring the sound energy that actually stresses those delicate hair cells in the middle frequency range.
That's the perfect way to put it. Now, once we have that accurate intensity measurement in dBA, we have to add the second critical factor, duration.
Time.
The ultimate damage is all about the total dose of energy the ear receives, which is a function of both intensity and how long you are exposed.
And this is the concept of equivalence, right? A huge dose in a short time is just as bad as the same dose spread out over a long time.
It is. The risk is statistically the same. This is what regulators use. They calculate what's called the ALEPD, which is the equivalent continuous daily personal noise exposure level, and they standardize it over an 8-hour working day.
Okay, so let's use that equivalence to really show how scary that 3 dB rule is. If the standard is, say, 85 dBA for a full 8-hour shift,
then every 3 dB jump you make halves the amount of time you can be exposed.
So 85 dBA for 8 hours is the same dose as 88 dBA for 4 hours.
And 91 dBA for 2 hours.
94 dBA for just 1 hour. It drops off a cliff.
It does. I mean, if you're exposed to 103 dBA, you have less than 8 minutes before you've hit your maximum dose for the entire day.
That is shocking. So to calculate this dose, assessors use a few key measurements. The main one is the LAQ, which is the average level over a certain time.
Right, and we use that LAQ to calculate the LEPD, that final 8-hour daily dose we compare against the legal limits.
But the sources also say we need to measure something called LC peak. What's that for? Isn't the dose calculation enough?
That's a great question. The dose, the LEPD, is about that cumulative fatigue, long-term damage. The LC peak, on the other hand, uses C weighting, and it measures the maximum instantaneous sound pressure. It doesn't care about duration. It's for the sudden, sharp impulse noises.
Like a dropped steel plate or an explosion.
Exactly, a stamping press. That sharp pressure spike can physically rupture your eardrum. It can damage the tiny bones in your middle ear, the hammer, anvil, and stirrup, long before your inner ear even feels the cumulative dose. It's a completely different damage mechanism.
So dose is fatigue, peak is trauma.
That's it. And understanding those mechanisms tells us why this all matters. Sound waves go down the ear canal, they vibrate the eardrum, which moves those three little bones. They act like levers, amplifying the vibration and turning it into pressure waves in the fluid of the inner ear, inside the cochlea.
Which is that snail-shaped thing. And that fluid moves across, what, about 30,000 tiny sensory hair cells?
That's right. And excessive noise puts physical stress on all these parts.
Wow.
But the real long-term cumulative damage is to those sensory hair cells. They get battered, they get distorted, and eventually they just deteriorate and die. And they don't regenerate. The loss is permanent.
Which leads to the different kinds of hearing loss. You've got conductive hearing loss, which is that physical breakdown like a ruptured eardrum. Instantaneous, traumatic.
But the one we mostly deal with in occupational safety is sensory and neural hearing loss. That's the damage to the hair cells from long-term exposure. And it often starts with warning signs like tinnitus.
That persistent ringing or buzzing in your ears when it's completely quiet.
Yes. And the most common precursor to permanent damage is what's called a temporary threshold shift, or TTS.
That's when you leave a concert and everything sounds muffled for a day or so.
It's the hair cells being fatigued. And what's really important is that TTS shows up in hearing tests as a noticeable dip in hearing sensitivity, almost always centered around the 4 kHz frequency.
Why there specifically?
It's believed to be due to the resonant characteristics of the ear canal itself. That 4 kHz VIP is the classic signature of early noise-induced damage. And if you keep having those TTS events day after day, they stop being temporary. They become a permanent threshold shift, or PTS.
And when that PTS starts affecting your ability to hear human speech, that's when you get a diagnosis of noise-induced hearing loss, NIHL.
Right. You can hear sounds, but you lose the clarity. You can't distinguish conversation.
Okay, so we know how to measure the dose and the peak, and we get the consequences. So that brings us to the legal framework. When does an employer have to step in?
Well, regulations set up very clear tiered action levels. Using the European and UK frameworks, which are pretty robust, the first trigger is the lower exposure action value, or LEAV.
Okay.
That's set at 80 dBA for the daily dose, or 135 dBc for the peak. At this level, the employer's job is about awareness. Information, training, and hearing protection has to be made available.
Made available, so it's the employee's choice.
It is. But then you hit the next level, the upper exposure action value, or UEAV. That's at 85 dBA for the dose, or 137 for the peak. Now it's serious.
So what happens then?
Measures to reduce exposure must be taken, engineering controls. And if those don't work, hearing protection becomes mandatory.
That gap from 80 to 85 dB, it's only 5 dB, but that represents more than a 3-fold increase in sound energy. That seems like a really small window between available and mandatory.
It is. It really reinforces that exponential risk. And above all that, there's the absolute feeling, the exposure limit value, or ELV, 87 dBA. No worker under any circumstances should ever be exposed above this level.
Even with hearing protection on.
Even with hearing protection, it's the absolute limit at the ear.
So how does this work in practice? How do you even know if you need to do a full assessment?
There's a simple rule of thumb. If you have to shout to be heard by someone who's just 1 meter away, and you're doing that for more than about 30 minutes a day, the noise level is probably over 90 dBA. A full assessment is definitely needed.
And for that, you need proper calibrated instruments, an integrating sound level meter for fixed spots or dosimeters for mobile workers.
And that calibration piece is non-negotiable for compliance. You have to calibrate before and after you use them every single time and get them professionally certified every 2 years. If you miss that step, legally, your data is worthless.
Right. So once you have the numbers, you move to the most important part, The hierarchy of controls, the systematic approach to fixing the problem.
Absolutely. And you always start at the top with the most effective control. Reduce the noise at the source.
Eliminate or substitute.
Yes. The sources give some great examples like instead of using loud riveting guns, switch to welding, or replace noisy diesel engines with much quieter electric motors. Simple, effective changes.
And one of the simplest controls here is just good old preventative maintenance.
It is often the cheapest and quickest win you can get. A machine gets noisy because it's inefficient, worn parts, lack of lubrication, something's out of balance. Just doing this scheduled maintenance reduces the vibration that creates the noise. You're controlling it at the source.
Okay, so if you can't eliminate it, you move down the hierarchy to controlling the transmission pathway. I love the physics here, especially with isolation.
Isolation is all about stopping the mechanical energy transfer. You use things like heavy-duty springs or high-density rubber mounts to decouple the machine from the building structure.
So you stop the entire building from becoming a giant low-frequency speaker.
Exactly. Then you've also got the inverse square law distance. It's free protection if you have the space. In open air, you get a 6 dB drop every time you double your distance from the source.
And then there are acoustic enclosures and barriers.
Which need to be very well engineered. They have a heavy, sound-reflecting outer skin and a low-density, sound-absorbing inner lining like mineral fiber. They can give you a huge reduction, maybe 10 to 30 dBA.
But the weak point is always the seals, right?
It's the practical reality that ruins the perfect science. A 1-inch gap for a conveyor belt, or a door that doesn't seal properly. That tiny leak can cut the enclosure's performance in half. They have to be airtight.
We're also seeing more futuristic stuff, like active noise cancellation, ANR, where you generate an opposing sound wave to cancel out the noise.
Yeah, you see that in high-end headphones and even some cars now. It's very effective for low-frequency, constant noise.
And then, as the last resort, you control the exposure at the receiver, at the worker.
That's things like building acoustic havens, like a quiet control room, setting up mandatory hearing protection zones, and critically, limiting the time a worker spends in the noisy area, which ties right back to that dose calculation.
Which finally brings us to PPE, the last line of defense. Plugs, muffs, they all have their pros and cons.
They do. And you also get specialized types, like flat response protectors for musicians, so they hear everything clearly, just quieter. Or level-dependent protectors that only block loud, impulsive sounds.
Okay, but here's where it gets really interesting. You can't just pick the one with the highest noise reduction rating. When you're calculating the actual protection a worker gets, you have to make a mandatory adjustment.
You do. You have to add a mandatory 4 dB factor to the worker's predicted exposure level at the ear.
Wait. You add 4 dB, so you're sourced to assume the protection is 4 dB worse than its lab rating. Why?
Because the lab ratings are achieved in perfect conditions. The 4 dB is a mandatory real-world discount. It accounts for an imperfect fit, beard stubble breaking the seal on earmuffs, sweat, a worker not inserting earplugs correctly. It's a built-in safety margin.
Okay, so what does this all mean for the person choosing the PPE? The protection has to be adequate, but not too good.
Exactly. The goal is to get the noise level at the worker's ear to somewhere between 75 and 80 dBA. If your calculation, after adding that 4 dB penalty, shows the level at the ear is less than 70 dBA, the protection is unsuitable.
Because it leads to overprotection.
Yes. And that is a huge safety risk in itself. If a worker is too isolated, they can't hear warning shouts, they can't hear a reversing forklift, they can't hear a fire alarm.
It's a paradox. You give them so much protection, they can't hear the things that could kill them.
And their natural response is to take it off for a second to hear something, and in that second, they get the full damaging exposure.
So to recap, we've got this logarithmic scale, the noise dose that balances loudness and time, the difference between peak trauma and cumulative damage, and this whole systematic hierarchy of controls. The science is incredibly precise.
It is, but the whole framework depends on human compliance. And that brings us to the provocative thought from our sources. The data suggests that almost half of all workers who suffer from hearing loss, they don't tell their employers.
Half of them. Why?
They cite perceived negative attitudes, fear of being moved off a job, fear of isolation, or just embarrassment.
So if the science gives us this incredibly precise physical framework to manage the risk down to the decibel, what does it tell us that the biggest roadblock is actually social and psychological?
That's the question, isn't it?
We can measure the physics perfectly, but the human element, the fear of reporting the damage, is what's compromising the entire system.
It suggests the solution isn't just about quieter machines or better PPE. It's about building trust and better communication. We really encourage you to look up some of the HSE noise calculator tools. They can help you apply this dose knowledge in a really practical way.
Thank you for joining us for this deep dive into what is really a silent epidemic. We hope this knowledge helps keep your ears safe